We present Physics-Guided Shape from Template, an algorithm for reconstructing the 3D geometry of dynamic cloth motion from a monocular video sequence. We use a pre-trained physics-informed neural network to realistically simulate a given cloth template forward in time to match every frame of the target video. Then, rendered images are computed by a differentiable rasterizer and compared to the target images. The differentiability of all parts makes it possible to employ a gradient-based optimization scheme in order to achieve high-quality reconstructions. Compared to most shape-from-template or non-rigid structure-from-motion algorithms, we do not assume constraints like conformal or isometric deformations, but rely on a physics simulation that is much more realistic in the case of soft bodies like cloth. The fast simulation of our neural network speeds up the shape optimization by more than 2 orders of magnitude compared to the state-of-the-art physics-based shape-from-template algorithm phi-SFT while preserving similar quality. Our method requires a video sequence of RGB and mask images together with the intrinsic and extrinsic camera parameters. Moreover, a template mesh of the initial state is needed for the neural network to perform the physical simulation. Our algorithm starts by initializing physical parameters of the cloth and external forces acting on it to some realistic default values. These values will be optimized in an iterative process and determine the shape and motion of the reconstructed geometry. All physical parameters and forces as well as the mesh vertex positions and velocities are used by a pre-trained physics-informed neural network to simulate the cloth forward in time. This network is the heart of our method as it has to produce accurate, smooth and stable predictions for the cloth geometry based on various influential input parameters. Let's look at the training procedure in more detail. The network takes the cloth state given by vertex positions and velocities as well as necessary internal and external parameters and returns the acceleration of the mesh vertices. These accelerations are then used to successively update velocities and positions similar to an implicit Euler integration scheme. It is trained in a physics-informed manner without the need for any external data from simulations or real-world observations. The training loop starts by initializing a training pool consisting of many flat cloths with random physical parameters and external forces within predefined ranges. A random batch is taken from the training pool and simulated for one time step using their individual parameters. The simulated cloths are then added to the training pool, thus filling up with more and more realistic configurations. The loss function consists of several energy-related parts that penalize motions that stretch, bend, or shear the cloth. All of them are modeled by quadratic potentials like in analytical physics simulations. Note that these terms do not enforce hard constraints like isometric or conformal deformations but rather balance them based on their energy. Moreover, external forces such as gravity and wind are collected in an external force vector for each mesh vertex and at each time step. A corresponding loss term is given by the sum of weighted dot products between external force and predicted acceleration. Lastly, we need an inertia term that penalizes rapid movements. Without this contribution, the network will immediately push the cloth into the rest state within a single time step. During training, the total loss will be minimized, which causes its gradient with respect to the network output to vanish. We can expand this expression in the way shown here, replace the energy gradients by their corresponding forces, and the derivatives of the positions by the squared time step due to the Euler update scheme. After differentiating the remaining parts and rearranging the terms, we can see that our neural network recovers Newton's second law of motion. Hence, we ensure that our neural model produces realistic simulations for the reconstruction task. After generating the simulated geometry at the desired points in time, we employ the differentiable rasterizer NVDiffRast to render images using the known intrinsic and extrinsic camera parameters. The texture is taken from the first frame of the ground truth sequence, and we assume an initial UV map to be provided as part of the template mesh. The UV map will be fine-tuned during the optimization process to account for initial mismatches. The generated renderings are compared to the ground truth images by computing the L1 norm. We use both the RGB and mask images for the loss function. For each image frame, we propagate the loss gradients back to the cloth parameters and the UV map, and simulate the sequence again with updated parameters. We evaluate our method on the phi-SFT dataset, and compare it to the phi-SFT algorithm, which also uses a physical simulation. In summary, we achieve similar quality as phi-SFT but only need a small fraction of the time. Due to the fast physics simulation by a neural network, we speed up the reconstruction time by a factor of 400, from several hours to only 3 minutes. Nonetheless, we retain a reconstruction of temporal consistent and smooth surfaces, which is usually not the case for methods without a physical simulation or similar techniques. As usual for these reconstruction tasks, the obtained mesh geometry enables further applications like novel view synthesis and scene manipulation. We analyze the importance of features in our approach by ablating one feature and comparing it to the full model. The largest differences occur when we only allow a constant external force for all vertices or when we remove the UV map optimization in the scenes shown here. The ablation is less noticeable in the remaining scenes or for different features but still decrease the reconstruction quality. We refer to the paper for the full ablation study. We show the stability of our method by optimizing the cloth shape 40 times longer than necessary. Our network behaves well when encountering distorted cloth geometry, and this stability consequently applies to the whole reconstruction pipeline. Thank you very much for your attention. Check out the video description for links to our project page and the GitHub repository.